In this lecture, we will see what are residues. Now, in order to find or define what is a residue, let us first move on to the Lorentz expansion of a given function f of z. Now, the Lorentz expansion of a function f of z is defined this way: a naught plus a1 to z minus a plus a2 z minus a the whole square plus so on, and the negative powers of z you can see. Now, this is called the principal part, which involves the negative powers of z, and this is called the analytic part, which involves positive powers of z. Okay, so now this Lorentz series can also be rewritten this way. We can also write it this way, because summation n takes the values from 0 to infinity, an into z minus a the whole power n, plus summation n running from 1 to infinity, bn by z minus a the whole power n. N will not take 0 here, because the moment I give n equal to 0 here, you will not have negative powers of z involved here. So here n will go from 1 to infinity. Now, in some textbooks, you can find the Lorentz series expanded in this way in a general form. This is nothing but this case where you have positive powers and negative powers. Now, when you look at the function f of z, you can see that these are the analytic part is where the function is well behaved and it is well defined. Whereas when you take the principal part, you can see that the function is not defined at z equal to a. So I know that for this given function f of z, z equal to a is a pole. Okay, have that in mind. Now let us just go through the statement. Suppose if I have any closed curve C around this point A such that f of z is analytic inside and on the closed curve C except at this point, then integral over C f of z dz is equal to b1. So generally when we talk about residue is meaning is a leftover. Now, why do we call it as a residue? Just look at this. Now, what does the statement say? It says if C is any closed curve around this pole A such that, I know that when I say pole A, it will be like this. You will have a small neighborhood around it. You know that only at this point A, the function is not analytic. Whereas in the neighborhood, the function will be analytic. That is what it means. Now here it says if C is any closed curve around A such that f of z is analytic inside and on the closed curve C except at A, then integral over C f of z dz is b1. Now what is this b1? Just look into the expansion, the Lorentz expansion for a given f of z. b1 is nothing but the coefficient of 1 by z minus a. Okay. So what does it actually mean? When I just integrate this function f of z over the closed curve C, it means we integrate all these terms. All these terms are vanished, leaving only b1. Integration along of a constant along a closed curve will become 0. And this analytic part, by Cauchy's integral theorem, when you just integrate analytic functions over a closed curve C, this will also be 0. And these terms from B2, okay, you can see that n takes higher powers greater than 1. Okay, all these terms will also vanish. So the only term which is left out after integration will be just b1, which is the coefficient of 1 by z minus a. Okay, so b1 is called the residue because it is the leftover. So what is happening here? When I just integrate this entire expansion, all I have is just b1, which is called the residue, which makes contour integration easier. In the forthcoming videos, you will know how contour integration is made easier using residues. At z equal to 0 for the given function f of z is equal to e to the power 1 by z. So how are we going to expand this? We have done this question earlier. F of z can be represented as 1 plus 1 by z plus 1 by z the whole square by 2 factorial plus 1 by z the whole cube by 3 factorial, and it goes on. Okay, so now you can see this function doesn't have positive powers of z at all, only negative powers of z it has. And what is the residue here? Residue here is nothing but the coefficient of 1 by z minus 0 in this case. So here residue will be just 1. Okay, this is one way of finding. Now there is also another way of finding using the limit. Now we know the pole formula. What does the pole formula say? Limit z tending to 0, z minus 0 into f of z, which is e to the power 1 by z. So when you find the limit, again here it is equal to 1. So this is how we find using the limit. And one more thing, here it is a simple pole, in the sense it's a pole of order 1. So residue for finding a simple pole is just the pole formula. If it is a pole of order m, we will have another formula which I will be letting you know. U at z will be f of z is equal to 1 by z power 4. Sin z can be represented as z minus z cube by 3 factorial plus z power 5 by 5 factorial, and it goes on. Okay. So here you can just bring 1 by z power 4 inside. So you will have 1 by z cube minus 1 by 3 factorial into 1 by z plus z by 5 factorial, and it goes on. Now what is the residue here? Residue is the coefficient of 1 by z. So here the residue will be minus 1 by 6. I want you to just try it using the limit and verify the answer with that. Okay, try this. Now let us move on to another question. Find the residue for z into cos 1 by z, okay, at the pole z equal to 0. So here, just expand this first. Z into, how do you represent it? 1 minus 1 by z the whole square by 2 factorial plus 1 by z the whole power 4 by 4 factorial, and it goes on. So when you expand this, you will have z minus 1 by 2 factorial into 1 by z plus 1 by 4 factorial into 1 by z cube. So when you check here, the coefficient of 1 by z here is minus 1 by 2. So the residue here is minus 1 by 2. F of z is equal to 1 by z into z minus 1. The poles are z equal to 0 and z equal to 1. Now, find the residue at the poles using the formula that is easier. So here, residue at z equal to 0 is obtained in the following way. Limit z tending to 0, z into 1 by z into z minus 1. So when you apply the limit, here you can see the residue is minus 1. Now for the other pole, that is residue at z equal to 1, in a similar way you can just check. Okay, just put z tending to 1 here. Here it will be z minus 1 and the given function. and the limit will be 1. You can just check it out. Let us quickly visualize this function in this picture. You can just see there are 3 closed curves given here, C1, C2, C3 for the same function. Now this curve C1 includes the singular point z equal to 0, whereas this closed curve C2 for the same function includes the singular point z equal to 1. And this is a closed curve C3 which includes both z equal to 0 and z equal to 1. So when you find integral over C1 for this given function f of z dz, the residue is at minus 1. You can see that there, the residue is at minus 1. Now for this closed curve C2, when we find integral over C2 f of z dz, then the residue is at 1. Now for this closed curve C3, there are 2 residues, one for the singular point z equal to 0 and the other for the singular point z equal to 1, because there are 2 poles here. Now let us look into this problem. Find the residue of f of z is equal to z square by z minus 1 the whole square into z plus 2. Now I want you to find the poles for it. There are 2 poles. One is a pole of order 1 and the other is a pole of order 2. So here we have z equal to minus 2, which is a simple pole, and z is equal to plus 1, which is a pole of order 2. So we are going to find the residue at these poles using the 2 given formulae. First, let us find the simple pole. So find the residue at the simple pole. Limit z tending to minus 2 z plus 2 into f of z. F of z is z square by z minus 1 the whole square into z plus 2. So here it would be, just substitute the value of z as minus 2 here. You will get it as 4 by 9. Okay. So this is the residue at the simple pole. Now coming to finding the next residue at the pole of order 2, use the formula. What does the formula say? Limit z tending to a 1 by m minus 1 factorial. So m will take the value 2 here. M takes the value 2 here. So just put it over here. You will have limit z tending to 1 by m minus 1 factorial. So that will become again just 1. Then d by dz of z minus 1 the whole square into your f of z. F of z is z square by z minus 1 the whole square into z plus 2. Okay. So you can see that this will get cancelled. So you will be just left with limit z tending to 1 d by dz of z square by z plus 2. So you will have to differentiate it once and then you will apply the limit z tending to 1. So I want you to differentiate and then you will just check the answer with this. I have used the quotient rule. Check this once and then apply the limit z tending to 1. So here the answer is 5 by 9. So we have 2 poles here. One is a simple pole and the other is the pole of order 2. For simple pole, I have used the first formula, and then for the pole of order m, I have used the second formula. So this is how you will calculate the residues at the given poles. Thank you.